Good morning. Welcome, everyone. Can you all hear me in the back all the way? Okay, then I won't have to use the microphone. Uh, we've got our live stream going in the background. So, again, if you go into Canvas, you could get onto it. Not that you need to be on it here because you see it live, but we'll see how that works out. This will be my first time since I think 2018 was the last time I used it. It worked pretty good. So. Um, We'll see how everything is working out technology-wise, but we're going to move into section 1.4, which is going to be about uh, calculating limits. So what we were talking about on Monday in 1.3 was really, they call it guessing at what the limit should be graphically. So we're going to go through a slight review of that and kind of do it. Today we learned some laws and properties and stuff about limits that will help us to kind of analytically do it, um, and we'll go from there. Uh, I did extend the introduction to WebWorks until Sunday because basically I'd like everything to kind of be a Sunday night due date so we don't have things popping up. I think it was due today or something and was cut off. So anyway, that's if you haven't finished it, go ahead and work through it. There is a check answers button, and it will show you which part is right or wrong, because I got a few emails and they said I'm putting everything in correctly. But sometimes it was a difference between a parentheses or a bracket. And when you look at those things, you think in your mind you put in the bracket and you put in a parentheses instead, so you don't see those things. I know because I don't see those things when I make those mistakes. Uh, but when you click that check answers button, it kind of highlights what's wrong and you can kind of focus real clearly. And that is one of the things with math is it's symbolic, but it's also very picky about which symbols you use uh, and what these mean. So today we'll work through a few examples. We'll look at the properties. Um, and this will all start in our textbook on page 35. So again, if you go into that, there's some examples that are in the textbook that are worked out. Those might be helpful to look through. They do probably more exhaustive examples than I'm going to be able to go through. Uh, but use those as your resource as well. So going back to what we had this as one slide from Monday. This is a piecewise function, and we wanted to calculate the uh, limits at the boundaries. So we went through using Desmos to graph it. To save us a little bit of time, I'm not going to go through that again. I'm just going to pull up the graph from Desmos and kind of speak about how we were, and this time I can draw on it, how we think about limits. And then we're going to apply that to how we can calculate limits when we know what the functions are, and we can kind of see there's going to be a connection. And if you ever are not quite sure about your answer that you've done sort of using the calculation tools, just come back and go ahead and graph it and kind of put the two together. Okay. In fact, we'll do one check that way. So what we're doing here, if we want to find the limit as x goes towards, let's see, what is it? It's a boundary at -3. Okay, it's working. So here's -3 on the x-axis, right? So we're looking basically from the left and the right. And so if we come from the left, what we're doing is we're tracing along this upper part of the graph, and we're seeing where's it going to. And so we're not actually going to -3. We're getting just very close. Maybe knocking on the door of -3. And what we see is that takes us the limit would be this number here, the y value of 9. Okay, so that would be a left-hand limit. They put a little -3 up in the corner, so that's coming from the left. If we go from the right, that's going to be the limit as x goes to -3 from the positive side. And again, we do that, there's a different graph. So now we're down here on this side because we're going from the positive side towards -3. And again, we don't go to -3, we just knock on that door. But this time we see that the right-hand limit would lead us to believe that it was -3. So we've got a right-hand limit of -3, left of 9. And since they're not the same, we would say that this limit at -3 does not exist. Okay, but that's we have to check both the left and the right, and that's kind of all we're doing with the graph. And we'll be able to do this with all the types of limits we're going to do. And then we could also check the limit at 1. We would do the same sort of thing, just looking both on the left side of 1, the right side of 1. And we also see that they're not the same, so the limit doesn't exist. So they're not continuous. And we're going to find later when we're doing derivatives that when that happens, we can't take the derivative at that point. Okay, so this is kind of identifying places where we're going to have some difficulties. Is that okay? Okay, good. So then there's 5 problems in 1.3 that hopefully you started working through. Again, everything's due on Sunday night. However, you might, if you can keep up with things, Friday we'll talk about 1.5, and tonight, or after this, there's, I think, 22 questions in 1.4. Although some of them are a little bit briefer, and with these techniques we're going to have, you might actually be able to do them a little bit faster than those 5 we were doing there. So let's just kind of talk about the laws of limits. And we'll start with the ones, I'm doing a little different than the textbook as far as the order. I'm going to start with the limits we can kind of talk about and check and kind of make sense about. And then we'll go to the more abstract laws. Okay, so the first one, these first 2 actually, and notice they're labeled 7 and 8, so we're into the list. We skipped 1 through 6 so far. But the first limit is if we have a constant, where C is a constant, then the limit at any point, when x is any point along there, that it's going to be the same constant. Because really, what is this function? What is the constant function? It's y equals c. It's a horizontal line. So every y value along that is continuous. Every y value is that number c, whatever it is. So it just sort of makes sense that as I go towards any particular x value, the y value is always going to be c. Okay, so we could look at the graph and that's going to happen. And the other one is kind of along that same line. This is the limit of x. And again, what we want to think is that's a function, or that's an equation, y equals x, right? That's really what we're saying it is. It's the f of x equals x. And that function, when you graph it, is I guess I'll change colors here, is the 45-degree line that cuts through like this. So when x is 1, y is 1. When x is 2, y is 2. That's that function. And so it makes sense whenever we get to any particular value, we call it a. When the x value is a, the y value is going to be a. That's how that function works. Okay? But this ends up, when we think about limits, remember, or maybe not remember, but you've got to think about limits. It's not really what's happening at that value. It's not what's happening at a. It's happening as we get close to a. And I had someone come up and said, well, if I just plug in a or plug in the value, I get the right answer anyway. And yes, a lot of functions that work that way, especially when they're continuous and all this sort of stuff. But what we're kind of just, okay, we're going to play the game. Let's build this concept. Okay, yes, when we've got continuity. As we get close to a, we could actually go to a and it's going to be the same value. But again, we're thinking we're not actually at a, we're just at the boundary. Okay. So with those first 2, we're going to build on those. Do both of those seem to make sense so far? Okay, so it's just, yeah, one's a horizontal line, the other's the 45-degree angled line, and they kind of make sense whenever we put those in. The next one is kind of building on this property 8, right? That if it works for y equals x, if I take an exponent onto x, and really, again, this is the function y equals to x to some power, that the y value is going to be what really all that's happening is I'm taking a number, plugging it to x, and I'm raising it to that power. So if I put a in for x and I raise it to that power, that's what the y value is going to be. Okay, so again, it really comes from the algebra concept. If you plug in a number and that you get the output, that's really what's happening. But what it's telling us is limits sort of work that same way when we have this continuity and stuff. And so as we really get close to x value of a, the y value is going to be a to that power. And that power of n could be squared, cubed, fourth power, fifth power, whatever. Okay? And again, does that sort of make intuitive sense? Okay? So we're getting good at how limits behave and work. One more. If it works for powers, square roots will work, because what is a square root? It's just a fractional exponent. Okay. Now again, when we're using radicals, though, they do make the nexus whenever we're using an even, right? Like a square, a square root. You can't have a negative inside there. So the concept is that the function has to be positive. Can't be negative because we get imaginary numbers. Okay. But again, it behaves the same way as an exponent, because this really, we could write this as x to the 1 over n. That's a radical, okay, instead of the radical n. That's all it is. So those all fall in, and they sort of say, yeah, I can agree with this because I can sort of see it, I could graph it, and I could go there and it'll be all good. So now we're going to take a look at each of the laws that are a little bit more abstract, and we're going to see how they work. But they're really based on these 7, 8, 9, and 10. So now we're going to look at 1 through 6. I think that's what we're going to do. Oh, actually, I think I skipped. I went someplace else. Yeah, we're going to look at number 6 first. So we don't go to 1 yet. So 6 really follows from, which one was it? It follows from number 9, right? So this one here, if we just have x to the n, then it gets a little more abstract because we're just talking about a general function. And again, this could be a trig function. It could be any function. But what this law now says is the power law is if we take that whole function, whatever it is, again, abstraction, and we raise it to a power, it will have its limit will be the y value of that function to that power. Okay. So that's really what we're doing. We take, it sort of makes sense, but again, we've gone to an abstract level because we don't know what the function is. We can't really picture it. Could be a trig function, could be rational function, could be multiple things. But and again, they call it a power law. But so part of what we do though is if you were math majors, we'd be busting out proofs right now probably. Your engineer majors and science majors and applied majors, we sort of say, okay, somebody's looked it over, and if they call it a law, it's a law, right? So we'll follow it, and it works, and we'll take it, but it does seem to make sense because of those ones we looked at, okay? And then 11, again, it's based on that radical rule that we had, and they call it the root law. And again, it really is just based on, it's the power law, but using fractional powers. And again, it just has the caveat that whenever we're using an even index, that the function has to be positive, otherwise we end up with imaginary values. And we don't want to talk about imaginary values, at least not right now. I don't think we do it at all in this class, but maybe we do. Sometimes you have to do it when you're in electrical engineering. They actually use imaginary values. So far, is it all making kind of sense? Okay. And all I've done is these are just screenshots out of the textbook. So if you go to the textbook, you'll see these laws. But again, they present them in a different order. They go to the abstract and then to the concrete. I always felt it was easier to just start with the concrete, what I could see, and then, okay, then let's go to abstract. So now we'll go to 1 through 5 is what they start with. And these are really, because they have a lot of power, and there's what we're going to use for the most part. So they've got this first one. And again, this is just a screenshot. And it basically says if you're going to add two functions together and take the limit of that result, you could do this, you could find the limit of each function individually and then add those limits together. Okay, that sort of works. And again, we're getting into some more abstraction, but it's just saying the sum of the limits is equal to the limits of the sum. We'll see the words in here. Again, intuitively it may make sense. And again, what that's going to allow us to do is take something like 2x squared plus 3x and view that as if it were that it could be viewed as a single function, but we could also view it as a sum of two functions. So sometimes when we get stuck, what it's going to allow us to do is take these, to break up, if we got things added, we could break it up and take the limits separately, and then we just add those results. So it kind of simplifies. Rule number 2, or law number 2, is the difference law. And again, it makes sense. If it worked for addition, it should work for subtraction. And it does, because subtraction is really just the opposite of addition. It's a takeaway instead of a put together. Okay. So again, we could either subtract the functions first and then take the limit, or we can take the limit of each of the pieces and then we would subtract those limits. Okay. And we'll work through some of these examples, but these are what we're going to refer to. Number 3, if we have a function and multiply by a constant, then the limit is just going to be, again, the y value, whatever the limit would be for just the function, multiplied by that constant. So it's kind of like, because isn't that what would happen inside? Inside the limit, we're first really finding a y value, and then we're multiplying it by a constant. So if we found that limit, well, what is the limit? The limit is a y value, and then we multiply it, we get the same result. Okay, that's all it's saying. But again, it gives us a way to, sometimes those constants can get a little messy, so we could just sort of set it aside. Let's work on the limit part in a simplified version, and then at the end we'll multiply. This law says we can do that, and we'll get the right answer. Okay. We've also got a multiplication law. So if we're multiplying two functions, we could multiply them first, and sometimes we might want to do that, multiply them out. Or we could take the limits individually before we multiply, and then when we've got the limits, multiply them together. And again, remember, the limits, what we're getting a y value. And so it's kind of like we can do it now and multiply inside here, figure out what y's are, and then multiply. Or we can go over here and figure out what the limits are, and then multiply them there, and we'll get the same value. Okay. And finally, there's this one with quotients, division. If we've got two functions that are being divided, same type of deal. We can break it up and do them individually. But again, since now we're dealing with a division, one of the things we have to make sure is that yes, sir.
This only applies when x approaches the same a, right?
Well, a will be the same in each of those, yes. Now, we're going to look at some other examples, and they tell us that what we'll look at is the function, as long as the functions are similar everywhere else except at a, we don't have to have it that certain things will happen. But yeah, generally what it's saying is that now the functions themselves could have different limits at a, right? But once we've got those limits, we can either multiply them, divide them, or go forward. But yeah, they should both, if they both have to exist. If one of the limits doesn't exist at a, we're stuck, because you can't multiply unknown times 5, right? That doesn't get you anywhere. Good question. Okay. So that's the lesson. Now let's look at some examples. Well, actually, I got one more slide. So here's if you want to take these 5, and again, this is just a screenshot from the text. There's the sort of the verbal response of what they're doing. So the first one is the limit of the sum is the sum of the limits. To me, this gets like poetry, and actually gets me more confused if I try to read too many of these things. The symbolically, but I've gotten used to the symbols. Sometimes you look at the symbols and it's just, wow, what's that? The limit of the differences is the difference of the limits. So again, you can either do it inside the limit and then take it, or you can do it the other way. If we're multiplying by a constant, we can take the limit with the constant, or we could move the constant out and say, let's do it later, multiply by the constant at the end. When we're multiplying, we can either, again, do all the work inside and then take the limit, or we can break them apart. That might be easier. Take the limits individually, we got our numbers, and then just multiply them. Same thing with the quotient. So we're not quite ready. We've got a couple more concepts, and then we'll get into some examples. So, and there's the names of them: sum law, difference law, constant multiple law. Because some of them, I looked in WebWorks. At least one of the problems it asks what property you're applying. I wouldn't try to memorize these because it doesn't, just know that you can do them. But what are they called? I don't know. I just use them, So, but if you want to know, some people, oh yeah, that's the product law, or that's the quotient law. So then there's this one. This is one that Monday someone came down and they said, hey, when I just put it into the function, I get the same value as you're getting with all this work to get a limit. So why can't I just plug it in? And that person was anticipating what we've got today is this called the substitution law. Whenever we have a polynomial or any rational function, we're actually able to do that because the way polynomials work is they're continuous and everywhere defined. As long as we're in the domain of the function, we can just plug it in. That's what the substitution law says. So now, yes. And what's kind of cool is it reminded me is sometimes when I would study math, I would see these patterns and I'd say, wow, I could just do this. I just invented something new. Turn the page and then that's when the book explained it. So I didn't invent something new, but to me it felt like it. I discovered something on my own. The book eventually clarified it for me or verified it. But so that's kind of cool. And you may get that experience as you work through and you say, oh man, isn't it easier just to do this? Why can't I just do this? Oh, I can do this. There's a law that says I can do it. So I thought that was kind of cool. So this, it just says if you've got a function that's a polynomial or a rational function, and A is in that domain, and that's why we have you do all these in algebra about talking about domain. As long as it's in the domain, we can just plug it in, and that's the limit. Okay, we don't even have to talk about trying to get close to it. We just say that is it. And again, we'll work through some other examples. And then this last one is kind of getting at what was brought up earlier. If two functions are equal everywhere else, except maybe not at that particular value, at that A that we're going to look at. And this is actually, we'll look at some of these examples. Then what ends up happening, if they're the same everywhere else except at A, then we can say that their limits at A will actually still be equal. And this comes into when we had a rational function, and if one of the factors kind of cancels out, what we end up with a hole there. And what we're going to see is that's the same thing as if we were to consider a function that was basically the same with it canceled out, that doesn't have a hole there. And so those are everywhere else they're the same except that one has a hole, one doesn't, but their limits both will be the same. Okay, so there's a rule for that, and I think that was the one we were looking at. And then we've got a couple theorems, and again we'll look at these. There's I think only one question that really gets into these, but these are various. Let's see, what's the first one? Okay, so the first one. We've already really talked about this. This is just saying that both the left limit and the right limit have to be equal for there to be a limit. So they're just formalizing it now. If they aren't the same, there is no limit. Okay, that's it. The next two are sometimes we can't take a limit of a particular function, but it might actually exist. And what we can do is if we can find a function that's bigger than it, and actually the second one is to squeeze one bigger, one smaller. And if they have a limit at that point, then what we know is the limit of the function we're talking about is bounded by that. Um, so this first one says that if our f of x function is always less than the g of x function, less than or equal to it, um, and then and again, it doesn't have to actually be everywhere, but just as any place when we're near a, um, that they will both exist um, as we get close to a. It doesn't say they'll be the same, but it just says if g has a limit, f has to have a limit as well, because it can't go off to infinity because it's less than g. So it's got a ceiling to it. So at least we know that there will be a limit. Doesn't help us find what it is, but it tells us there is a limit. Now, if we find two functions, one smaller and one bigger, and the bigger and the smaller function go to the same value, it's called the squeeze. So if these two functions are functions somewhere in between, these two other functions will squeeze it into the same limit. Okay, so sometimes we can use that. Again, there's a couple examples in the textbook. Knowing which functions to use takes a lot of experience. I always don't get it right the first time. The good news is the example we have to do in WebWorks is pretty manufactured, and we're going to apply this, but we don't have to figure out what functions are bigger than and less than the other one. So we're kind of given that, okay, because we're given them. But it's called the squeeze function because, yeah, you've got one below, one above, and they go to the same limit, so our other function has to go there. But again, we use this one if we've got a function that we really can't, there's no tools that we have that give us an answer of what the limit might be at a particular place. Okay, how long? We go till 3:30? 3:30. 3:20. Okay, yeah, no, not a minute more, not a second more. Okay. In fact, I apologize for being late on Monday, but I made up for it today because I was more than a half hour early. Of course, I thought class started at 2, and I thought, man, I'm running behind. But anyway, we're here. Okay, so now let's start looking at some examples and see how we might apply these. And again, you'll start to look at this, and maybe intuitively you'll just say, yeah, that seems like the right answer, right? So they want us to take the limit as theta, the variable theta, goes to pi over 2. So that's the value. And so what we can do is what we've got is we could look at this as three functions that are being multiplied. So you could break that up, and I'll just do a little shorthand of the limit of 8 times the limit of theta times the limit of sine theta. And again, each of these is as theta goes to pi over 2. But again, I'll mess myself up if I try to write too many details. But we know they're all going to pi over 2. Well, what's the limit of 8 as theta goes to pi over 2? 8. Good. Because it's a constant. So that's we applied the constant law or whatever. What's the limit of theta as theta goes to pi over 2? Pi over 2. Because theta is just like that function x, right? So we're going to multiply this by pi over 2. So far we would have 8 pi over 2 or 4 pi, right? But we're not done yet. We got to look at what would be the limit of sine as theta goes to pi over 2. 1. And again, it's not a polynomial function, but we know that sine is continuous. And so if we could play the game and just see what happens when we get close, but we'd see it's the same thing when we actually get there. This is going to be 1. So actually, we just now multiply all these together, and it's going to be 8 pi over 2, which is equal to 4 pi. Okay. So that's how this helps us. So again, we might have been, okay, what do I have to do? It might seem too much work here. Yes?
So would it be the same thing if you were to take the limit of 8 theta and multiply it by the limit of 10 theta?
Exactly. Yeah, because there was another one that says we could have taken that 8 and just kind of said, okay, it's a constant, let's take it out. And yeah, so there are multiple ways we can do it. You got it. You got it. Okay? So you'll see this, so you'll get where you'll kind of just calculate. You won't have to write all this out or, yeah, so the thing is we could have said, well, this is 8 times the limit, right, of theta times sine, because that's a constant, and then you don't have to even worry about that, and then just multiply by 8 at the end. So all those work. So far, so good? Yes? Yeah, exactly. We could have looked at that and say all of these exist with that pi over 2 and it's continuous. I can understand. So yeah, let me just put it all in, figure it out, and then, well, then I've got a constant. What's the limit? It's 4 pi. So yeah, exactly. Multiple ways of doing things. Okay. Here's another one. And we've got a rational function. So what's the one thing we have to worry about or take for, I don't know, worry is the right word, but the denominator, we got to make sure of our domain, right? -3 is not in the domain. But notice we're not going towards -3, we're going towards +3. So we're kind of like cool here. It's not going to cause us any kind of problems. So again, we could just say the limit of x squared plus 6x plus 9 all over the limit of x plus 3. Do it individually. And you could, if you want, break it down with the sum rules in there. So, I mean, you could break it down to all the little pieces. Yes? We'll get there because that causes problems, right? Because it's not going to exist in the denominator. So we've got a couple. Sometimes it's going to mean that the limit actually doesn't exist at all. We got one of those. Sometimes the limit actually does. And so good question. I think I've got 2 or 3 examples like that because, yeah. And so again, what we could apply, remember we have that one that if it is a polynomial, we could just evaluate the polynomial so we don't have to get all this stuff. And both of these are polynomials now. And so I could just plug in 3. So it's going to be, the limit will be really just 3 squared plus 6 times 3 plus 9 divided by 3 plus 3. So I go and do the calculation. And again, I've got a law that says I can do it, but I figured I could do it anyway, right? So then what, that's going to be 9, no, 3 squared is 9, 18, and another 9, so that's 18 and 18 is 36 over 6, which I think gives us 6. Okay, so yeah. So we start to see, this is feeling a lot better. Now, yeah, we could have gotten the graph and we would have seen that as x goes to 3, the graph is also going towards 6. Okay, we could have done that. Not so bad anymore, right? Okay, so now we're getting to a place where we have this question. And what you see is this one, x goes to 4. You might not see it right away, but if you factor the bottom, you're going to get one factor of x minus 4. And I think the other one is x plus 7. X minus 4, sorry. And x plus 7. 4 times 7 is 28. The top, though, and so yeah, we look at this as x goes to 4, x minus 4, that's going to be a 0. Whatever the other term is, so we're going to get a 0 in the denominator. Okay, now we're sort of stuck, but let's see what happens in the top. So then we factor the top, which is also going to be, let's see, I think this is x minus 4 and x minus 7, how it's going to factor. Okay. And again, we're still taking the limit of this whole thing or just the limit of the top and the bottom, but we can't really take the limit of just the bottom because we're going to get division by 0. It's going to be undefined. So what we are able to do is remember, there was that one where I have the 2 functions, so I'm thinking of the top and the bottom, and they're kind of equal everywhere else except at maybe one point. Well, what happens is when we take x minus 4, we can cancel them out. But now we've actually got a different function because now we don't have the problem of 4 not being in the domain. Okay, so this becomes x minus 7 over x plus 7, and we're looking now at the limit as x goes to 4. And what we're using is that property that we've got a new function, a similar function, but it's going to give us the same y values everywhere else except at positive 4. So there was that rule. And so we can take a limit since the y values are the same everywhere else we're going to say that these limits will be the same. And again, I can break it down, limit on the top, limit at the bottom, or I could just say, well, they're both polynomials, right? So I can just evaluate, I can use that substitution law, and that's going to give me what? Negative 3 over 11. So our limit to this thing is going to be negative 3 over 11. Now, if we graph it, what we'll see that the function we started with actually has a hole at negative 3 over 11, right? It does. The other function, this one over here, will be identical to it right on top, and it doesn't have a hole at 4. Wait. The hole would occur at x equals 4, y equals negative 3/11. Yes. Yes, exactly. So if we can, and that, so to answer your question earlier, if we can get, we got to somehow use some techniques to get the 0 part out of the denominator. If we could do it, it'll exist. If we can't, it's not going to exist. So that's a straight line. So because sometimes we can't, and we got one example in here that is one of those. So far, so good? Yes, sir.
So do we have to factor it always, or do we
Um,
require?
Not necessarily. Sometimes that's I mean, to me, it was easier as I was saying the 28, so that's what's going to happen is we're going to get canceling when we factor and goes. You also could have just graphed it and you would have seen, hey, it's still continuous there. In Desmos, if you would have went to that point where x was 4, it would show you have a hole, but you would say, hey, I remember there's a hole here, but the limit's going to exist. So you can combine all these techniques we've been using. Yes.
When does it become like a vertical asymptote?
Good question. When we can't remove that 0, then we're going to get a vertical asymptote, which means the limit doesn't exist because usually one side will go to infinity, the other side goes to the other infinity, and we've got that in here. Good. In fact, that's this one. Okay, so this one, same type of deal, right? We look at that, we got x minus 7. If I go to 7, I'm going to get a negative, I'm going to get a 0 in the denominator, undefined. And I might think it's going to be a asymptote, but these other ones have been holes, so which one is it? So I look at this, oh, can I factor? Well, 1 plus 7 is 8, but no, this, if you might be able to factor it, I don't know, but I don't think so. But it doesn't factor into, there is not a factor of x minus 7 up there. So it's not going to cancel out. And actually, I don't think it factors at all. I don't like to say with certainty because sometimes I'm wrong. But this is one I'm going to say, hey, I don't see any way to get that x minus 7 out of there. It's not going to factor out. That's really the only tool I have at this point. So I'm going to say it's undefined, but I don't really feel confident about that because I'm going to say, maybe I'm missing something. So we might go to Desmos and graph this, and which we could do. And what you'll see, this one is when you first graph it, it's because it's so far out, you see one part and it's kind of, well, what's really going on? There's another part up there, so when you zoom out, you see this. Okay, so I did it in advance just to kind of show you, this is where we've got an asymptote because we can't get that x minus 7 out of the denominator. So as we go to 7, one side's going down to negative infinity, the other side's going to positive infinity, there is no limit. Okay. And this is the way I would verify. Now I feel comfortable. I can put the answer, no limit, doesn't exist. But before it was like, well, maybe I'm just missing something, right? Maybe there's some other trick I forgot about. But nope, that's all there is. So again, use the graphing part. It's such a powerful way. And I remember because when I was, I sound like my grandfather now. In my day, we didn't have those graphing calculators. We didn't. When I was in the early 80s, we started having some HP calculators, but we had one line. We didn't have any graphing stuff. So we couldn't look at these things, and so we had to learn all these rules and stuff. We got graphing calculators now, let's use them, or Desmos, let's use our tools, especially with all the color and all the stuff we've got going on. And then again, over here, we say at the table, so you set up a table, you plug in 7, you see it's undefined. And then what I did is I looked to the left and the right, and I saw that they're going in different directions. One's really big negative, one's really big positive. Okay, that's what's happening. Okay, good. Got about 10 minutes, but not too many more. So this is kind of what we're getting towards, and we'll use this to build up to the first concept of what a derivative is. This is actually called the difference quotient. It's taking y values basically in the top, x values in the bottom, and what h is we'll use it as a variable. One is x plus h, one is x. But anyway, that we let h go to 0. What we're doing is we're getting 2 points and turning them into 1 point, and we're getting the rate of change at a point, instantaneous rate of change. That's what this is all set up for. So that's why you'll see a few of these. But can we let h go to 0 here? Not right now, because then we got division by 0. But so now we try a few tools. We've got up here, we could just kind of FOIL this thing out. So a plus h squared, so we'll get 3. I'll do that separately. Is going to be a squared. What is that? 2ah plus h squared. So I just FOILed that out. Minus 3a squared. You'll see that a lot. Still over h. And again, we are taking the limit, but we'll distribute the 3 through. So we get 3a squared plus 2ah plus h squared minus 3a squared all over h. Combine like terms. What's that? Oh, thank you. I always do that. And it's not just h squared, it's 3h squared. So I didn't distribute. Thank you. Yeah. See, that when I'd love to have people watching over my shoulder because I always there we go. So that's a little bit better. Okay, so good. Okay. And then we can say, okay, in the top, and what this is doing is that we're getting a limit of a similar function. We're simplifying a function. So minus 3a squared, positive 3a squared. And then at the same time, each of these has an h, which I can factor out. And just for purposes of time, I'm going ahead and do that in one step. So I take the h out. We have 6a plus 3 over h. And again, we're taking the limit still. Yes. Thank you. I tell you, I get in a hurry and I make all sorts of mistakes. Sometimes I'd say I'm on purpose, but they just happen. Okay. So good. Keep me honest. And then now that the h's cancel out, right? This is kind of factoring and expanding and all that kind of stuff. Can we take the limit of this thing now? Certainly. We now have a polynomial function. Just stick in 0 for h, 6a. So whatever a is, our limit is 6a. Okay. And what we just did is we took our first derivative. We'll learn that this is a derivative, and we'll find derivative rules and such. But yeah, we took the derivative of 3a squared, and what we'll see is actually all we'll have to do in the future is 2 times 3 gives us 6. That this is the derivative we came up with. But we use limits because what we really did is we took 2 points and made them into 1 point. So we'll find ways to get instantaneous rate of change, but it's going to be easier once we get past this part. But this is just kind of giving us some feels that this is all possible. In this one, a little bit more complicated because we have 2 parts of a function. We're letting t go to 0. So both of these, if we separate this with the difference rule, both of them are going to 0, and we have division by 0 in both cases. So actually, we don't want to use the difference rule or law at this point. What we actually want to do with this one, I think it just takes some experience, is we want to find a common denominator. When we're at it, then we can subtract them, and what we'll see is we'll actually get some things canceling out, and then it'll work. Okay. And just to be transparent here, these examples I'm working I took out of WebWorks. So this is we've been doing our homework as we go through. The thing is you'll get slightly different examples, but you get something for this particular problem. When you hit this one, you'll need to use the same technique, but it may look a little different, or it might not. We don't know. So the common denominator you can kind of see is this part. We could factor out the t, and then we've got t plus 9, and we've got a t over here. So this one can stay as it is. This one we need to multiply the top and bottom by t plus 9. And then we have, now we've got a common denominator. So then in the numerator, we get t plus 9 minus 9, so that minus goes there. In the denominator, we have t times t plus 9. Plus 9 and minus 9 is 0, so we're left with t over t times t plus 9. And then we can cancel out the t. Again, we get actually a different function, but we're using that one property that this is a simplified function. So now this one we can actually go ahead, and this one we can take the limit as t goes to 0 of 1 over t plus 9, because if we stick in 0 now, it's just 1/9, right? It's not undefined. So this limit is going to be 1/9. The original limit was also 1/9. But again, a technique we had to get through because on the surface, it was looking like they're both going to an infinity. But if we graph it also, again, we would see that what ends up happening is, as at 0, it's actually going towards 9. We get a hole there, but 1/9, sorry. So graphically it would appear the same too. We okay with that one? A little more complicated. Almost there. This is the one. This is the squeeze play, or the squeeze law. And again, it's actually a lot easier than coming up with something. So we don't know what function they want us to take the limit of, but they're telling us our function, whatever it is, it's always larger than this function, and it's always smaller than this function. And so as long as those two functions have the same limit at the point we want to go to, which is 0, as long as they have that same limit, what they're going to do is they're going to squeeze our function f of x to have that same limit too. So this is, yes? Then we don't know. What we might be able to say is we would know that the limit would be in between them. That's kind of there's these corollaries to the squeeze play. So it's sometimes you get that, and okay, we can put a boundary. We know there's a limit, but it's somewhere in there. But if they go to the same, we can actually get the limit. But good question, excellent. So again, we can take a look at the limit as x goes to 0. We've got negative, actually, I'm just going to go ahead and distribute that -2, right? And then this other one, limit as x goes to 0, x squared minus 2x minus 4. Plug in the zeros, this limit goes to -4. Plug in the 0, this limit goes to -4, so it satisfies that rule. Since the smaller function goes to -4, the larger function goes to -4, there's no place else for that other function in between to go to. So its limit is -4. Yes? We would say it's indeterminate. There could be a limit, but those functions aren't going to help us get it. You can if yeah, there is a corollary on that. And wow, we made it. So finish up, again, everything I moved all due dates till Sunday. We've got 1.3, hopefully finishing up that. 1.4, there's 22 questions. We did some of them together. You'll see how they work. And then on Friday, we'll get to 1.5.